Morning, everybody. It's a real pleasure to be here today. Kieran actually described me as Dr. Tom Blewitt. My mother wanted me to be a lawyer. My dad wanted me to be an engineer. He won out. I became an engineer, but didn't get to the doctor level. No, that's fine. I'm very happy to be here today. Yes, I've been at UL almost 43 years now, what the interesting thing about UL is that it's a company that sees lots of new things coming through the doors, and the new technologies, new challenges, and so forth. And as the years have gone on, the challenges sometimes they're paradoxical. It's like you have to trade off and see what's the right balance. And sometimes it's situations like what we're going to talk about today, which is highly complex, and it really requires a level of rigor that perhaps even at UL, we haven't always had to follow based on the types of products that we've seen. But increasingly, we're seeing more and more complex products coming in, and so we're a standards development organization as well as a testing, inspection, and certification organization. So we, as an organization, have to keep up with the technology, up with the challenges in the marketplace, and what's happening today in order to exercise the thought leadership that the company has been known for. So today I was asked to talk about autonomy, autonomous vehicles, and with the very provocative question, really, are autonomous systems safe? And I'll take a shot at that, and we'll see where that goes. But I do want to also speak then about some of the standards development activity that we have around autonomy, which will help ultimately, perhaps you folks in the room and others around the world, to be able to answer that question. So again, great pleasure to be here today. Let's see. The clicker is not advancing, so I'll just hit enter the old-fashioned way. So the talk that I'll provide today, I'll start off, and I will give an answer on this question: are autonomous systems safe? Then I'll talk a little bit about this UL 4600 standard, which is the standard for evaluation of autonomous products. I'll talk about the difference between products and systems. I'll speak about where 4600 fits in with the other standards, the ISO 26262 and the additional ISO standards that are out there. We'll speak about the importance of a safety case, and that's essential to what 4600 is seeking to do. We'll look into a little more detail on what a safety case is and how it ought to be constructed. Then I'll talk about the standards development process and really the mechanics of it, but also really how you folks can get involved. And that's a key thing here. One of the reasons why I come out and talk to you folks is to get as many minds to the table to help us come up with safety standards that have the benefit of all the wisdom of folks such as are in this room. And then I'll close with a few thoughts. So my clear answer to whether or not autonomous systems are safe, it's yes, no, maybe, and I'll go a little further than that. But it's in the eye of the beholder, right? I think I think we could agree on that. Is there a safety case for yes? I think so. If you think now with the technology that's in existence today on board of vehicles, for sure the technology can improve upon us as drivers. We're tired, distracted. We may not respond as quickly under all the various driving conditions. We sometimes make incorrect decisions. We might get mad at somebody on the road. There's a whole host of things that are inherent in us as people that the technology doesn't have. So the technology, first off, can see much more of the environment. It doesn't have the blind spots, theoretically, that we have. It's always paying attention. It doesn't get distracted. It's always on and always looking. In many instances, the reaction time is much quicker and more decisive than the human operator. And then as we more fully realize these capabilities, the technology is going to reside not only in the vehicle you might be in, but also the vehicles around you and the infrastructure over which you travel. And all of that will help also avoid accidents. So for sure, the technology today, and we see it, these vehicles are on the road, it does work. And so a safety case for yes can be made. However, you can do the same on the other side of the fence. Exact same graphic here, but now look at these things and say to yourself, how robust are these systems? Oh, okay. Go ahead. Yeah, there you go. I was on autonomous mode. Oops, speaker, microphone, audio test. I don't want to do that. Waiting for others to join. I'll need some more assistance. I don't want to hang up on the audience. So I just been advancing it with the. That doesn't seem to be working. Okay, so I think I'm good, right?
Yes.
All right. So the folks, I guess, that are online, they're going to see me starting with no. I did have a case for those folks for yes, but for the audience here, the safety case for no is again goes back to how robust are these systems, how thoroughly have they been vetted. Do they really work under all the possible scenarios that we need them to work? And what happens over the life cycle of the vehicle as well, when people maybe start substituting parts, or they wear, or what have you. Kids hit the car with a basketball, something like that. So you could say that there's a case for no as well, right? Are autonomous systems safe? Okay. So enter doesn't work any longer. So let me hit this one. Let's try that. No. That's no. Oh. Okay. It looks like it's. Let's see. Okay, I think I got it. All right. So yes, no. Now the question here is, what do others think? So the National Transportation Safety Board came out with a report in November in which they looked at this question, and they in particular they studied the unfortunate incident that happened a year ago in March in Arizona, where somebody was killed, and they studied this situation pretty thoroughly, and they issued a report. I understand you folks will get a copy of the presentation, so there's a link to that report on the bottom of the screen here. And they made a number of observations and a number of recommendations. I guess this is a transition. I highlighted some content from that report. So the NTSB found a lack of federal safety standards and assessment protocols. So so you could say that they're making a bit of a case for maybe. They didn't say they're unsafe or safe, but there's a lack of these protocols. The National Highway Traffic Safety Administration has inadequate safety assessment processes. So again, a maybe. And then, as many of you know, the vehicles also have to be permitted to be used on the roads within a state. And the NTSB also found that the states have minimal or no requirements for these vehicles. So the argument here is that they're not certain. They're for sure the information available to them to be able to make a definitive answer to the question is lacking. There was an incident, and there are others where perhaps the technology didn't work the way it was expected. Or there may be other factors, but the reality is that so there is some evidence there. And then the question is even what ultimately is safe? Is one fatality unacceptable, or 33,000, or whatever the number is today? And where do things fall within that? So these are all questions that have to be answered. These all have to be decided by society. But the big question here that the NTSB basically has raised is how adequate a job have we done collectively to make the case that this technology is safe? And so this is really the premise behind the UL 4600 standard. Our standard is intended to help make the safety case, provide structure and help organize the thoughts around what will constitute a sufficient safety case. The scope of the standard is it covers safety principles and processes. The processes, risk mitigation, tools, various techniques, life cycle. But basically, it's a principles and processes standard. So it's not a standard that tells you here's an absolute safety level or number. It tells you how to go about doing the calculation, the analysis. And it's intended to do these, put out these principles and processes for evaluating the safety argument that the producers of these vehicles and the regulators and the like might put forward to say that they're safe and that they're able to operate in autonomous mode. The other thing here, we're 4600, and I'll go into the differences between it and other standards in the marketplace today. The other thing here is that 4600 is really focusing in on full autonomy, so the human is out of the loop. There's no safety driver. There's no expectation that the last minute the human's going to ride in there and save the day in the event of some condition occurs in the marketplace. And so that's not to say that these vehicles can't have a provision for somebody to actually manually operate it, but the standard is aiming really at full autonomy. And it addresses a whole host of elements that go into making the safety case. You can see some examples up here. Safety case sufficiency, I'll talk about that. Talks about metrics and feedback and how do you continuously validate over the lifetime of the vehicle, let's say, and the systems of the vehicle that the safety case is continuing to be proven or that it needs to be improved upon. And so I'll go into a number of these details here. So the thing is, though, and we've had this question asked of us at UL, is where does 4600 fit in a world that already has ISO 26262 or the ISO publicly available specification 21448? And there are others documents out there as well. And our point of view on this is that we're looking to complement these standards. We're not looking to duplicate them, replace them, interfere or conflict with these standards, but to essentially to fill in certain needed gaps, if you want, such as were identified by the NTSB. Our standard 4600 is what they call an ISO a Type A standard. It's the highest level. It provides for basic concepts, principles, and the like. It's a basic safety standard. In ISO, there's Type B and Type C, and the Type C are the product-specific and very, requirement, thou shalt not do this or you shall do that type standards. So 4600 is pretty high up in terms of providing, again, these principles and processes. And more specifically, it differs with the ISO 26262, for instance, which is, if you're not familiar with it, it's the standard for road vehicle functional safety. And it's been around, I think, 20 years or so. It's a derivative of an IEC standard, 61508, which is the mother of all functional safety standards. And so 26262 looks at electrical and electronic functional safety, specifically the components, the electronics, and electrical devices. And it's looking at whether they perform their intended function and that they perform their intended function under fault conditions. It could be component faults or other types of faults that are inherent in the design or manufacture of that particular component. Looks at design faults as well, and that can include the software, the programmable elements that are part of those devices. It also looks at what measures for error detection and protection and the like that are inherent on the chips and the boards to basically supervise for the faults that may occur and to be able to correct for that. So it's a very much, it's not only a hardware standard, but its origins were in the hardware and the reliability. You have a certain input and you expect a certain output. Do you get that? How reliable is that input and output association? But in the real world, for these devices and so forth, you need to do more than just look at that board level, the electronics, let's say. And this is what's driven the development of the 21448 standard, which is safety of the intended functionality, or SOTIF, as is safety of the intended function. And there, it's really looking at the system now, and not just the component, but the system, and to make sure that if it's a braking system, that it actually, in fact, brakes, and brakes under certain conditions and in an expected way. Where the 26262, if I got input 1 and I get output 1, I've met the test, so to speak, in theory. But SOTIF then takes it beyond that. Is input 1, output 1 equal vehicle has braked, in time. That's where SOTIF comes into play. And SOTIF, and then the 21448 standard, which is not actually technically yet a full ISO standard. It's what they call a publicly available specification. So it means it doesn't have a complete consensus yet in the international community. But it identifies scenarios. It identifies triggering events where the safety function may be initiated. And the current state of that standard today is really at the ADAS level, so the kind of the driver assistance. It's not yet looking at full autonomy. It may get there, but that's not where it is today. So again, so these are the ISO standards that exist. So what does 4600, the UL standard, do? And again, the title, Evaluation of Autonomous Products, and I'll speak to that in a second. But it looks at the safety case. So again, it's the overarching. Why is this going to be safe? Why do you consider it to be safe? Have you done your due diligence? Do you have the sufficiency of your analysis? Do you have your sufficiency of your evidence to ensure that this is safe? And again, as I mentioned earlier, it enumerates the principles and processes to go about making that safety case. It does address AI, although maybe in a bit of a limited fashion, but it's going there, whereas the other standards have some room to go yet. And then again, as I mentioned, the standard looks at full automation, and that's the SAE Level 5 automation. I want to make just a quick note on products. We've said systems and products, and we'll use the word item as well in here. This standard was originally developed with the intent to look at robotics, because UL sees a lot of robotics. But as we got into the development of the requirements around robotics, which might be the robots that move in and around an office like this, or in a mall, or in an airport, or more than just the robotic arms that you might see in an industrial manufacturing location. But when we got into that, we realized that all the same questions and issues exist, for autonomous vehicles. Only the more severe risks potentially here with the large vehicles moving at high speeds. And so for a completeness of this development of the requirements for robotics, it actually made sense to look at the automotive situation and say perhaps, okay, maybe for a robot that's running around your house, a little cuddly dog or whatever that chases after you or whatever, well, maybe we don't have to have as rigorous safety cases, depending on the nature. It's maybe a little more structured environment than the roads, or that the mass is not as great or the speeds are not as great. So we basically upped it to the vehicles, but this standard is actually more comprehensive in intent than just the vehicles. And so I think that's important. Product 2, it's a misnomer in a way in some of this because it's really systems. So product, we're using it in the broadest sense. And then in reality, even the systems, we want to use that more broadly because it's not just the physical device, but the safety case may include the processes that a manufacturer uses to get feedback and to tweak and continuously redevelop their safety case and redevelop their design, even if it's a software-enabled type of a design. So that's the point of the standard. But today I'm focusing obviously on the vehicle aspect of it, and I've used the word safety case multiple times now. So what is a safety case? So it's defined in the standard, and this is wording similar to as appears elsewhere, but it's a structured argument supported by a body of evidence, and that provides a compelling, comprehensible, and valid case that a system is safe for a given application in a given environment. This is a practice used in the medical device arena. It's used in automotive. It's used in aerospace. It's used in a number of places, and usually to help convince a regulator that one has done their due diligence and that the regulator is able to make sure that their needs have been met. And so traditionally, when you do safety cases, you're looking at manufacturers generating data, gathering specifications and other information that's available to be able to say, my product is safe because of this information that I have and the conclusions that I've drawn from that. They package all that up, they ship it over to a regulator or organizations like a UL, and they say, here's all my evidence and information as to why you should find an agreement, that you're in agreement with me that it's safe. And up to a point, historically, that's straightforward and all. And the fact that manufacturer A and manufacturer B don't put everything together the same way maybe is not that big of a deal when things are not that complex. But when you're talking about autonomy and all the details and the modules and the systems and the lines of code and all that's entailed there, you can see how this gets really tricky, right? So when you got very large data sets, lots and lots of elements that go into these systems in order to make them safe, it becomes really important to be able to actually organize this information, articulate it in a way that is clear, that it's consistent, that the regulators and others will be able to follow and be able to conclude with you that you've actually done an adequate safety case. So the safety case really is going to be the goals, the arguments, and the evidence associated with your claim that is safe. And then this standard, in part, helps structure the way in which you'll present that information. So I have here one example, and this is, the standard isn't prescriptive. You can attack this in different ways as long as it's you're following certain established conventions and your safety case is consistently organized. Here there's a couple of typos in here, but basically this is illustrating one approach to it in terms of goal structuring notation. And basically, again, you need to have a goal. The goal might be, and this is very simplified. There's an awful lot to this, but the goal might be that you have identified all of the potential hazards, and then those hazards been mitigated in some way or eliminated, and then you're going to have an argument as to, well, okay, what have you? How are you postulating that you've actually done an adequate job to identify all those hazards? And then, this may have one box here, but in reality, there may be lots and lots of these. And then ultimately, your argument, okay, I have identified all the potential hazards. Here's how I'm doing that, and here's my evidence that I've been successful at doing so. So this framework, if you want, is the objective to follow in developing a safety case. When it's fully articulated, this is massive, right? So this is, again, just look at this as only illustrative. So what actually is a safety case made up of? What are the things that you need to consider? How to articulate the goals, articulate the arguments, and articulate the evidence that's required? Well, you need those elements, right? Number one, sure. So in the case of goals and arguments, you have to be able to provide sufficient detail so that the accuracy of your goal, the sufficiency of your goal, the sufficiency of your argument is well supported. So that means in this standard here, since it's a safety standard, it does call for actually producing lists of all the hazards that you've identified, and to be able to go back and check on that list for its sufficiency. Also to make a list of the risks that you anticipate as a result of those hazards. Then you need to be able to identify and support these goals that you have. Again, you've covered them all. So it's not enough to say, all right, my vehicle in theory is capable of dealing with the hazards of a sunny day in California, and then have that vehicle in a snowy New York street or something like that. So it's so your goals have to be broad enough and complete to make sure that you're covering all of the hazards and risks. You have to look to avoid defects in your arguments. A lot of times, we say, well, we don't have a hazard or a risk, and you might articulate something there, but that may be limited, and so you need to be careful that you're not potentially oversimplifying or using arguments that have known gaps in them. And so the standard goes into details. It uses the word pitfall. So when certain types of arguments, certain types of evidence, certain types of approaches that people take, the standard actually does clue in as to where sometimes people underestimate the degree to which they need to make that argument or to support it. And then finally, that should say defective. Avoid inclusion of defective construction patterns. When things get really complicated, we engineers, we look for something where we did it before, and then you pick it up and you drop it into the new place, and that can work. But have you accounted for all the underlying assumptions? This is good. It worked over here, so I can bring it over to there. Is that always true? Have you even sufficiently analyzed that? And if there's a theme that you're going to hear from me here throughout all of this, it's analyze, analyze, analyze. Don't assume anything. Challenge, and then make your case in terms of providing evidence. And that's the other piece of this here: evidence sufficiency. So obviously, all your arguments. I've identified all the risks. I've considered all the hazards that are there. The mitigation means are robust. There's this, that, or the other aspect of the design and construction that's going to take care of the concerns that I have. Are each and every one of those supported by evidence? So the standard is basically saying don't leave any column untouched if you want. So if you identify something, there's no shortcut to okay, I don't have to worry so much about that. I'll talk about an exception to that, but in principle, the standard is asking you to follow the rigor. So and again, it's not telling you the answer. It's not giving you that list, but it's telling you how to analyze, how to carefully look at all these details. The evidence has to be, fit the argument, right? So if your evidence is incomplete or it only covers part of the argument, you haven't done a sufficient job of supporting it. And then it's logical here, but we produce a lot of evidence when we have it and a lot of data, but something that's tricky or difficult, we don't have as much. And the standard basically is equating all of the arguments the same, and the same rigor has to be applied. You may attack it differently. Your evidence may not be always reams and reams of data, but you have to take the same rigor to be able to look at the evidence, whether it's difficult or not. There are some situations where there may be accepted risks. Again, if the vehicle is only going to be used, on the streets of Maui somewhere and not, in northern Minnesota in the wintertime, you might be able to say, all right, I don't have to worry about whiteout conditions and so forth. And so there may be certain types of accepted risks that you might be able to build in, especially in these at this stage, the transition stage towards full autonomy. But then you need to validate that through gathering of data and feedback from the marketplace. Does that car somehow wind up, being shipped to Minnesota someday or New York or wherever? So it's important. You may start out with some accepted risks, but you have to come back and continuously validate to see whether or not those accepted risks stand up. Safety culture is spoken about in the standard as well, and this is really important because it looks at the management, the engineering and design, the manufacturing, the business aspects, all the different aspects of a company to make sure that everybody's role in safety and the safety outcome for things that come out of that particular operation is well understood, and that and that everybody understands. We've seen in the aerospace industry, that's been they've had some rough sledding recently, and because of the influence maybe of the business on some of these safety decisions. And so it's really important, and it's codified in a way in the standard by talking about the safety culture and at least specifying things to look for to make sure that that's present in those organizations. And then finally, of these characteristics, the item scope. So the item here, I'm using it as a euphemism for system or product, because it can include more than just the physical device itself, let's say, or a component or what have you, or the system of the vehicle, but it can include the life cycle and process controls and the like that exist outside of the vehicle itself. But all these things might contribute. So if you're doing over-the-air download of software, that goes onto that part, okay, well, what rigor, is put to the development and validation of that software that ultimately is going to show up in the physical device. So the item scope has to be well defined. You need to make sure that you've completely addressed all of the concerns with the particular item. And the last item that's on this list here I wanted to mention, because a lot of times we go, well, there's some things that are not safety related, so we don't have to worry about them. And so in the car, if the entertainment system, right, you know, if it normally displays a picture of your kid and it shows your radio channels and so forth, well, depending on what interfaces it has with the other systems of the vehicle, that may actually become a safety significant component. And so even though it's theoretically outside and it's you need to understand the context in which that component is being used. And where 99% of the time it's a radio and it doesn't bother anybody except for if you don't like the channel it's on, now it's maybe going to interfere with the safety of your vehicle. So you need to be able to look at that as well and include some of those types of components inside the scope. Okay, there we go. So, and then, you know, again, with the time allotted and so forth, I'm only really skimming the surface here. The standard does get into the details of risk assessment. It doesn't say that you have to follow a SIL, you know, or a performance level, you know, or any particular approach, but it does require you to actually to look at the integrity level and to be able, if you were making a safety case, to peg on one of them and then be consistently using that throughout your safety case documentation. The standard also, even though it's the autonomous vehicle, obviously it asks you to look at what's going on around and what might happen around the vehicle and make sure you take that into account. It looks at software and cybersecurity and those elements because they're all part of making sure that the safety case is achieved. Simulation is necessary for because you can't drive billions of miles into every scenario. Are your simulation tools accurate and robust, and so on and so forth? So each one of these elements that are here are to be looked at as well, and the standard gives a good amount of detail. The document right now in its draft form is about 300 pages, so it's a pretty large document. Off-the-shelf components, you go on down the list here. Let's see. There we go. Because this is an AI and machine learning group, I pulled out a few things that were in the standard. It's kind of obvious, but it does spell, you know, it does state these, makes these statements, and it has some detail underneath it in terms of what rigor you need to have in order to achieve this outcome. So machine learning basically has to obviously provide acceptable capabilities. So how you're using it, is it the right use for the machine learning? Is it constructed? Is it architected in a way that it'll give you the acceptable performance? Are you using, you know, appropriate, you know, learning examples and complete and robust learning examples? Have you taken into account the known errors? So if we all seen these vision recognition systems, you change a couple of pixels and it completely changes it. You know, so when your particular machine learning algorithm, does it, you know, is that a vulnerability or a weakness that needs to be addressed? And so you need to look at that. And then also post deployment. So great, it works beautifully, sort of out of the box. What happens when things are updated and changed later on? So the standard does talk about these. So a lot of obvious, but it's one of the few places where it's actually articulated in these automotive standards. Let me just take a couple of minutes, and then I'll stop for if there's time left for some questions. I wanted to talk a little bit about the standards development process. UL develops, I think it's like 1,600 standards now. We follow a process that really hinges on a consensus body known as a Standards Technical Panel, STP. And I'll explain what each of these mean in a second. The STP is a group of individuals representing a balance of interest categories. I'll explain what that is. These folks both develop the initial standard as well as do the maintenance. You know, as time goes on, the standards, they're living documents, they'll change. And these folks are the folks who ballot on the standard. So it's their decision as to whether or not it gets adopted as an American national standard. So in the case of 4600, we're following UL's process, which is accredited by the American National Standards Institute. So when it is published, UL 4600 will be an ANSI standard, an American national standard. I have on the bottom here, there's a mention of Canada. We also developed standards for Canada and the Standards Council of Canada under the auspices of their rules. Very similar to ANSI, some differences, but in this particular case at the moment, 4600 is not being put together as a Canadian standard, but we may follow up at a later date and do that as well. I use the word balance. What does that mean? Well, for sure, you don't want to have a standard dominated by one interest, which then drives it in one direction or another that may not be suitable for the marketplace. We have a goal that no one interest group be over 1/3. I use the word goal as opposed to a requirement because you may have a committee of a certain size and it exactly is balanced, and then somebody retires and you're out of balance, and that doesn't make the committee illegal. What it does is puts us on the clock to actually, get replacement folks to restore the balance of the committee. So we may actually, when we have a committee, have to restrict the size or membership based on that. So if we have an overabundance of manufacturers that want to join, which often is the case, if we don't have enough regulators and others, I'll show you what these other interest categories are, then they can't join. There are other ways to participate, but they won't be voting members. And then also, the rules don't require that there has to be somebody from each interest group. Ideally, you do. So the interest categories are the ones that I'm showing on the screen there. Producers means manufacturers. Supply chain could be manufacturers, but these might be the component folks producing components for use in an end product. So if you're in that situation, it's an end product standard, you could be considered to be part of the supply chain. AHJ stands for authorities having jurisdiction. Regulators, these are usually the frontline folks who approve a particular installation. Government would be the others who, like the federal agencies often, but not exclusively, that are more general, or they may regulate, but not product by product. Consumers, typically the members of our committees are consumer interest groups, but it doesn't, you as an individual, you can be a consumer and be a member of a committee. We have consumers on our table saw standards committee, for instance. And there's some others, and if you don't fit any one of these that are on the screen, you can be a general interest. These are self-declared, but people police that. So if you're a manufacturer and you say, I'm general interest or I'm consumer, and you're still working for a manufacturer, somebody will point that out. And so we do make sure that the integrity of this is observed. In the case of 4600, we have, I think it's 33 members. These are some examples of folks who are on that committee. You can see there's a pretty good diversity of insurance and manufacturers, there's universities, there are test labs, there's consumer, and this list can change and all that. So as with the membership on the committees, but it's the point here is really it's a pretty diverse committee working on 4600. The process itself is very straightforward. Somebody makes a proposal. Anybody can make a proposal. The proposal goes to the STP. The STP reviews that and then decides through a ballot whether or not it agrees or doesn't agree with that proposal. Oftentimes somebody ballots and says, I don't agree with that. There's a negative ballot, or there's a lot of comments, there's more work needs to be done, and that results in a comment resolution period. And then ultimately, whatever the resolution is, the document goes out for recirculation to see if people change their mind, or that maybe they don't like the changes that went into the standard, or maybe somebody's comment wasn't resolved to their satisfaction. There may be iterations of that, and ultimately the document becomes published as a standard. And so I'd say the key thing here is that whether you're a member of the committee or not, you all can make proposals. You're all able to comment. You're all able to be heard. The committee has to address your comments. So whether you're a voting member or not, your voice is equal to that of the voting members. You just don't get to vote if you're not a member. So anybody, and that's the key thing, is that you can participate. The committee itself, in order for a document to ultimately get published, there has to be consensus. And the consensus means that 2/3 of the voting folks have to vote for it, and then at least a half of the committee. So if there's 33, 17 members of the committee have to vote, and 2/3 of that 17 have to vote aye in order for the standard to be published. In the case of 4600, it's going to be balloted in mid-December is the plan. So I won't read through this because of lack of time, but this will be in the handouts, I think, or the information that gets sent to you. But this is how you can participate. UL has a lot of aids to help you get involved. And I'll close really here with the thought that that whether autonomous vehicles are safe or not, we want them to be safe. I think a great amount of the population wants these vehicles out there. I know certainly my dad would have loved that, when he stopped driving, and there's a lot of other folks for whatever their personal reasons, they want them there. And so we feel like at UL, in some way, we want to see this work. There's so much great opportunity here, and we want people to be comfortable and confident. We want the regulators, consuming public, everybody really to be comfortable with this technology. And in order to be able to do that, we just have to make our case. And I think in the case of UL 4600, there's a mechanism by which that can be done. So we encourage you to learn more about it, get involved, talk to others, and help us make the case for autonomous vehicles. With that, I'll stop and thank you.